Hi, and welcome to day 6 of Calc Applications. Our understanding goal is more properties to help us graph functions without the use of a GDC. So we have some more curve properties that we're going to talk about. We have stationary points. A stationary point of a function is a point such that f prime of x is equal to 0. So where our first derivative is equal to 0, we have what we call stationary points. It could be a local maximum, a local minimum, or a horizontal inflection. Turning points are your maxima and minima. So if we consider the following graph, which has a restricted domain of -5 to 6, point A is a global minimum, and it has a minimum value of y on the entire domain. B is a local maximum, as it is a turning point where the curve has shape and f prime of x is equal to 0 at that point. Okay, so what's happening is the graph, down here, looks like this here. C is a local minimum, as it is the turning point where the curve has shape and f prime of x is equal to 0 at that point. So again, we got shape of the graph. D is a global maximum, as it is the maximum value of y on the entire domain. For many functions, a local maximum and minimum is also the global maximum and minimum. For example, for y equals x squared at the point 0, 0 is a local minimum and also a global minimum. Okay, next page. Horizontal or stationary points of inflection. It is not always true that whenever we find a value of x, where f prime of x is equal to 0, we have a local maximum or local minimum. So for example, if f of x is equal to x cubed, the f prime of x is 3x squared, and f prime of 0 is equal to 0, or f prime of x, excuse me, is equal to 0 when x is equal to 0. Okay, so that's the graph that we have right here. The x-axis is a tangent to the curve which actually crosses over the curve at the origin 0, 0. This tangent is horizontal, but the origin O, 0, 0 is neither a local maximum or a local minimum. It is called a horizontal inflection or inflection as the curve changes its curvature or shape. Okay, so as you're coming along here, it kind of changes how it's curving. Therefore, this is not an actual turning point. It's not a minimum or maximum. It is a point of inflection where it changes curvature. Okay, so we have sign diagrams, which we've been doing, and we have to look at the graph that we have. The sign diagram of its gradient function is shown directly beneath it. We can use the sign diagram to describe the stationary points of the function. All right, we have a local maximum, a local minimum, a point of inflection, and you can see the signs on your sign diagram. So we have a stationary point. We have a stationary point, and we have the sign diagram of f prime of x near x equals a, and this is the shape of the curve at x equals a, or near x equals a. Maybe not x, exactly, maybe near. And we have a local maximum. What your side diagram is going to look like is we're going to have a plus and a minus. So we're going to be increasing, then decreasing. what that looks like on a graph. This is A. X equals A right here. So I'm increasing, I hit A, and then I'm decreasing. That's a max. A local minimum is going to be just the opposite. Negative and then positive. So again, where x equals a, I'm going from decreasing negative then to increasing positive. Remember, we talked the other day that the first derivative tells us where a function is increasing or decreasing. This is horizontal or stationary inflection. So what that would mean is that A, I'd have positive, positive, or at A, that should be A, I have negative, negative. So that would look something like this. Or something like this. Okay, this is constantly increasing, the first one, and I'm going to change from how the shape of my curve goes. And here I'm constantly decreasing, but I'm changing my shape. So that's negative to negative. So that's a point of inflection, not a minimum or a maximum. All right, for the first example, find and classify all stationary points, meaning there's more than one, f of x equals x cubed minus 3x squared minus 9x plus 5. So first of all, we have to take our derivative. And that will be equal to 3x squared minus 6x minus 9. Once I do that, then I need to factor it. So I need to find where it's equal to 0. So I take out a 3 as a GCF. And this is what I'm left with. And then factor again, we get x minus 3, x plus 1. This is where our number lines that we were working on the other day come in handy. 1 for each factor. We have 3, x minus 3, and x plus 1. All right, 3 is just a constant, and it's positive, so this entire number line is just going to be positive. X minus 3 is equal to 0 at 3, so to the left is negative, to the right is positive. X plus 1 is equal to 0 at negative 1, to the left is negative, to the right is positive. So when I put my number lines together, I have positive, negative, negative, which gives me a positive. And then positive, negative, positive, which gives me a negative, and all positives, which gives me a positive. So here my function is increasing, here my function is decreasing, and here my function is increasing. So at negative 1, I am increasing, then decreasing. So this is a local maximum. And that would be the point negative 1. If I stick negative 1 into the original function, I will get 10. And at 3, x equals, x equals negative 1 and x equals 3, I have a local min because I'm going from negative to positive, so it's decreasing then increasing. And that would be 3, negative 22. I found f of -1 by substituting in the original function. F of 3 is -22. Find the greatest and least value of x cubed minus 6x squared plus 5 on the interval -2 to 5. Well, let's take our derivative. So our derivative is 3x squared minus 12x. We have a GCF of 3x. So we're left with x minus 4. So when I do my number lines, I have one for 3x and one for x minus 4. So 3x is equal to 0 and x is 0. And everything to the left is negative, anything to the right is positive. X minus 4 is equal to 0 at 4. So everything to the left is negative, everything to the right is positive. Try that again. So 0 and 4. Negative, negative is positive, positive, negative is negative, positive, positive is positive. So my function is increasing, decreasing, increasing. So that means at 0 and 4, I'm going to have some sort of local min or local max. If I'm going increasing to decreasing, that would give me a max. Decreasing to increasing, I'd be having a minimum. So we need to find f of -2, which is one of our endpoints, f of 0, f of 4, and f of 5. That's my other endpoint. So if I substitute -2, I'll get -27. If I substitute 0, I get 5. If I substitute 4, I get -27. And if I substitute in 5, I get -20. So if we were to kind of map out what this looks like, -2, -27, and then I'm going to go up here to 0, 5. And I'm down here at 427, -27, and this goes up to 5, -20. So this point 0, 5, -27, no, sorry, -2, -27, and this would be 4, -27. And then this point here, our endpoint would be 5, -20. So which is the greatest and which is the least? Well, when we're looking for greatest or least, we're looking at our y values. So this is my greatest at 5. And at -27, they're both my least values. Alright, so we had local minimums, local maximums, and points of inflection that we learned about with the first derivative. If your sign diagram is changing, then you have a local minimum or local maximum. And if our signs are not changing on our sign diagrams, then we have a point of inflection. It's not going to change directions. All right, we'll talk about this in class.